coming. I'm probably between you and lunch, which is a challenge for me, so hopefully you can sit with me and also engage with me as we talk about what's happening in AI for weather forecasting. You'll notice two faces here. You'll notice only one face up here. I'll come back to that at the end, where we're going to show you where you can go and see Harrison and go and get a live demo of some of the things that I'm talking about. Thank you very much, a professional over there. So, we're going to be talking about data-driven weather forecasts. And first of all, let's have a quiz. Who has heard of ECMWF before? Have any hands? You have a few? Good, okay. But probably not everyone has, so let's go with that first. So ECMWF was set up 50 years ago. What was the idea? The idea was weather forecasting is a hard problem. Weather forecasting is a shared problem. The weather of your neighboring country is very similar to the weather of you, and so we should band together, particularly across Europe, to form an organization, an intergovernmental organization, to go about and try and address this really challenging goal. So this was happening around the dawn of the first era of doing computer-based weather forecasts. So this is where high-performance computing was just about to come onto the scene, and the idea was we're going to buy a big computer and we're going to solve the physical equations and be able to get a really accurate weather forecast. And this has been something that we've been working on for 50 years. And what we do, we provide our data to our national organizations. So there are 35 of them across Europe, indicated by these lovely colors. And so mostly you won't have heard of us, but you will have seen our data, maybe indirectly. So if you use the Météo France app, for those of you who live here in France, some of that data will have come from us via Météo France. So that's who we are. And now I want to go on to talk to you about how AI is not only transferring many of the applications that we've seen across a wonderful set of talks and booths, etc., but also having a big impact in weather forecasting. So I'm going to be talking to you about how AI for weather forecasting is helping us make weather forecasts faster, make weather forecasts more accurate, and also helping us make them more accessible, particularly for thinking about the global south. So, you might not know how a weather forecast is typically made using physics-based approach. Just to give you it in a few seconds, typically that involves a high-performance computing system. It involves a big rack of computers, maybe about 50 nodes of a supercomputer, and takes sort of 1 to 2 hours to go about making a forecast. So something that you certainly can't have in your own house at home. AI-based systems, which can learn from the massive trove of data that is in the weather and climate ecosystem. So that was one of the things I forgot to mention about ECMWF. So we are home to lots of things, including 1 exabyte of weather and climate data, which I'm sure everyone of you here at an AI event will know that data is really the secret to unlocking good quality AI-based systems. And so having trained on a lot of this data, these AI-based systems are capable of making accurate weather forecasts using only a single commercial GPU and in around 2 minutes. So what does that mean? That means a transformation of maybe like 1,000 to 10,000 reduction in watts, in energy used for kilowatt hours, in energy used to perform a forecast, and a dramatic reduction in the infrastructure required to be able to do that. So, what about accuracy? I'm not sure you've all maybe seen it. We've all got frustrated with our weather forecasting apps when they've failed to predict rainfall and you've been caught short without an umbrella. But weather forecasting have been getting a lot better consistently over a long period of time. So this plot is trying to show the evolution over multiple decades in how accurate weather forecasts are. So accuracy is on the y-axis. We're trying to aim for 100. The different colors are just a few different metrics. You don't need to worry about them. And we're seeing the improvement across these different metrics across many decades. And you can see that the line is on average always going up, but you can see that it's going up very slowly. And what those lines are that cover the whole decades are these physics-based approaches. That comes from a better observing system, that comes from cleverer use of high-performance computing, that comes from better physics models, better representation of our physics on those computers. And then right at the end, we have AI-based models entering the workflow. And we can see that for all of these different metrics, these are a noticeable jump in forecast accuracy. And this is something that will not be realized by a physics model tomorrow. This is something that's probably a decade or more of physical developments to even get there. So you've got something that's dramatically cheaper and also something that, even extrapolating the developments in physics-based systems, is maybe a decade-based away. The cool thing is that this is not really about getting rid of physics models, because the training data for these AI models is very much based on the output of these physical models. So we use physical models to create the training data, but we can envisage a system that can then be far cheaper and more accessible to run. So what does this mean for more accuracy? That accuracy chart maybe didn't really connect home. So an example that would obviously be known to a lot of people as an important use of weather forecasting is hurricanes or tropical cyclone prediction. And here I'm showing a case from the Pacific for a tropical cyclone, where you can see that the black is the observed track, the red is the machine learning-based track, and the blue is the physics-based track. And you can see at this point, quite early in the trajectory, a long way away from landfall, the AI model did a better job. Now, a single case study is ripe for cherry picking, but on average, we see that these AI-based systems are around 12 hours more accurate, or give you 12 hours earlier warning of where those events are going to make an impact. So that's 12 hours earlier to possibly make a decision on what needs to be done, an evacuation, aid being brought in, or other interventions. So, the lovely thing about being an intergovernmental organization is that we don't necessarily have to be doing anything for profit. And so underpinning our AIFS, which is our data-driven weather forecasting model, is a Python-based framework for building these weather forecasting systems. This is called Anemoy. It's a fully open source. It's how we build our machine learning weather forecasting models. And it's also something that we're not working on alone, but working on with many of our partners across the European meteorological landscape. So many of your national Met services, depending on where you live in Europe, are representing in this lovely circle, and we're working together to go about building this framework and building state-of-the-art data-driven weather forecasting models. Along with compute, you'll also, along with data, you'll obviously know that compute is another key part to be able to do this. And this is where it's been great to work very closely with Euro HPC systems to be able to scale data-driven weather forecasting training out to hundreds to 500s of GPUs, and able to build sort of these state-of-the-art models across Europe on the wonderful infrastructure that is Euro HPC. So what is the primary data source, and why are these models able to succeed? Well, as part of the Copernicus EU program, ECMWF have built a data set called ERA5. So this tells you what the weather was like every hour of every day, at every point in the globe, back from 1940 to present day. And so this obviously gives you a wonderful source of data to be able to train a data-driven weather forecasting model. And so then you have a lovely data set to do supervised learning and say, here's the state of the weather now, please predict me the state n hours in advance. And then apply that model auto-regressively to be able to move out arbitrarily far into the future. So within Anemoy, we've been building multiple different modeling capabilities that you can train all from the same framework. So this includes global weather forecasting models and also limited area. Why do you want to run a weather forecast over a limited area? You maybe have high-resolution data sources, so you're able to make a more accurate localized forecast, for example, showing here at a European scale or at a Scandinavian scale in this middle section. Where the future is actually going for this is to supplement physics-based model data with observation data, which is what's being referred to there, where we're starting to use satellite data to get a better constraint on how we can do more accurate weather forecasts. So I'm sure you've all looked at your weather forecasting app and seen that it's never a yes, no on almost anything, particularly when it comes to rainfall. This is a chaotic system. The butterfly effect is in full motion, and so we need to be providing users with probabilistic information to be able to provide reliable decision making. So we've built sort of two different data-driven weather forecasting systems. One of them is called AIFS Single. So this is about giving a single best estimate of what the weather's going to be like over the next 15. But actually more impactful is an ensemble-based forecasting system. This is where you launch a load of trajectories, and within them is meant to capture the truth of what's actually going to happen into the future. And then you can see where these different members of the ensemble are going, what is likely and what is less likely to happen. And this is another place. This is done by a sort of akin to a Monte Carlo approach. And so this is something where the reduced cost of data-driven weather forecasting models is again very valuable, where currently we can run with 50 simulations of what might happen in the future. For the same sort of energy, we can think of that being 500, 5,000 different simulations, and so do a better estimate of getting the tails of the distribution, getting those rare events, seeing them a little earlier in the forecasting. So another view on how accurate this is an assessment of forecast skill as a range of different time. So the time is on the x-axis and the skill is on the y. Lower is better, and you can see that the AIFS is again about 12 hours more accurate, so giving you an earlier glimpse into what's going to happen for surface temperature against both the physics-based system, but against also some of the other wonderful contributors that are in the field. Some of you might have heard already of this revolution because there've been some press around Google building some of these data-driven weather forecasting models themselves. So what's next? What's the next frontier? I've talked to you about data-driven weather forecast, where we're focused on atmospheric dynamics. However, we live in a coupled Earth system. So within the EU flagship program Destination Earth, we're expanding these data-driven atmospheric models to give a holistic picture of the Earth system evolution. So this is about building data-driven forecasting systems for ocean and sea ice dynamics, for land surface processes, for waves, and then hydrology concerning rivers and flooding. And the goal is to build both individual systems for each of these that can then be coupled together to allow you a flexible, modular approach to data-driven Earth system modeling, gaining all the advantages that we've seen from these machine learning models already. So allowing you to run things faster, simulate more often, build better estimates of your uncertainties of what's going to happen. So I'm just going to show you a few examples of where we are with our prototypes for these different Earth system components. Some of my colleagues are here around at this event to go and ask more details of, and we've also been writing some blogs describing this work in more progress if you want to dig into the technical details, which are going to come up a bit short here. So here's an example for forecasting soil moisture. So how much moisture is going to be in the land itself, which has big impacts for agriculture, amongst other, and showing what's happening over the spring transition into summer, where you can see that Europe in general is drying out. And this was an event that was very well forecasted by this data-driven weather forecasting system in forecasting, particularly France, but over Europe in general, there was a fairly extreme drying of the Earth system. So waves are also a big impact of Earth system modeling. Accurate wave forecasting is important for coastal impacts. It's important for shipping and other industries on the sea. And this is something where we've also been able to show that we've built some really accurate data-driven weather forecasting models, data-driven wave forecasting systems. So here I'm showing a video of a relatively extreme wave system that was propagating across the Pacific. The nice thing if you're based in Hawaii is the upshot was some lovely surfing conditions, not that I was there. But what you can see here is the data-driven weather forecasting model and the operational physics-based model gave very similar predictions here, sort of despite the fact that it cost dramatically less to go away and make this wave-based forecast. Another example of the Earth system is hydrology. So here we're looking at stream flow down a river in a single basin, and seeing again we have an event occurring in time. So here we've got time on the x-axis, and then we're looking at the discharge along the river as we go along, and we can see that because there were large rainfall events, we had several spikes in discharge, we had several increased levels of water going down this basin, which could lead to flooding, and we can see the observed and then the data-driven simulated system giving you very similar results for this hydrology event. So again, this is a system where building from a mix of physics-based and observation data sources, we're able to create accurate data-driven forecasting systems. Another of these components is looking into ocean and sea ice dynamics, and here I'm going to focus on the sea ice, where we're showing the evolution of some data-driven sea ice forecasting systems over the Antarctic and Arctic. So what you can see here is a combination of the sea surface temperature, the sea ice fraction, so how much how much of a specific grid box is covered with sea ice. And then the red outline that you might be able to see if your eyes are particularly good is the true observation of where that line, where the sea ice boundary was. And you can see that most of the time, the models are doing a good job of capturing the extent and retreat of the sea ice evolution as we go through the seasons in this testing period of this data-driven forecasting system. So again, we've been able to create an accurate data-driven system, this time of the ocean and sea ice, training on this lovely combination of physics-based and observation data. So that's where we are now. We have these prototypes that are already showing great promise. Where we want to go next is to begin to couple these together on a routine basis to allow people to have a modular forecasting system that combine these systems depending on what your area of interest is. So if you aren't interested in sea ice applications, you don't have to have that forecasting system as part of your arsenal. I should say that in addition to making our forecasting framework, the Python framework, open source, we're also on a path to making open source models. So if you don't want to receive data from us, you can also go and take these models themselves, run them for better scientific understanding, or run them to make your own live forecasts if you have the right input data streams. And that takes me nicely to my last topic, sort of emphasizing the modularity of these solutions. So this is the concept we've been working on partly in Destination Earth of demonstrating how transformative the power reductions, the ease of movement of these forecasting systems are compared to their physics-based counterpart. So we've created an AI forecast in a box, which you can go and see at booth P2, where my colleague Harrison and colleagues will be able to run a demo for you. This is a system that's able to go away and prepare the initial conditions, so you can specify what day you want to go away and run a forecast. Most likely that's today, but maybe you want to run for some historical period to try and understand climate risks or for reinsurance purposes. So that then allows you to then run the model at the click of a button through a graphical user interface, and then specify what products you want. So I've shown you that weather forecasting models can be producing lots of different products, variables. You may only care about a small number of them for your specific application, so you can tailor what kind of plots you want to see to be most useful for you, and then those are then visualized for you. So the goal of this is something that you can deploy anyway. So we've brought a literal box to go and run it on, but this could be deployed on cloud infrastructure, on the upcoming AI factories, and make it easy to run and install. Where we're aiming for is a modularity in terms of models that you want to do. So currently we support a mix of sort of global and then regional modeling, but the next steps are going to be adding in these Earth system components so you can pick and choose and combine where these are. And so a little demo of how it's going to work. There's a variety of interfaces to go through in terms of being able to go with a very simplistic or highly customized version of what products you want to do. Do you want a deterministic? Do you want some probabilistic information on what your forecast is? And then being able to browse the charts at your leisure. There's some cool technology behind the scenes to come up with a task graph, which my colleague Harrison and others will be happy to explain to you, that breaks down these different item points depending on the products, depending on the data, depending on the model, and then goes and executes that task graph for you. So that's the end of my presentation, but I hope it's been interesting enough to get some questions. And if not, you can come, if you want to go and see that I've not accelerated some demo or cut out some shortcuts, you can come to P2, which is just over there, and get a demo live for yourself. So thank you so much for your attention.